Hello, my name is Jamal Tutur, and in this video I will summarize Lipizzaner algorithm. Lipizzaner is a method that allows resilient GAN training. In general, GANs present a machine learning method that trains two single models, a generator and a discriminator that applies adversarial machine learning to train. In contrast, Lipizzaner trains a population of generators against a population of discriminators applying a co-evolutionary approach. These populations are distributed in a spatial grid. Thus, in each cell we place a pair generator discriminator. Other co-evolutionary GAN training approaches apply an all versus all method, which means that they train all the generators against all the discriminators. That requires an important computational cost because of the quadratic complexity of this kind of methods. In order to mitigate this computational cost, in our case we distribute the training by defining subpopulations. These subpopulations are defined according to Moore neighborhood relationships. For example, if we focus on this cell, we call it the center, we can define its neighborhood by taking into account the north cell, the east cell, the south cell, and the west one. Thus, the subpopulation we will define it according to these cells. Another example could be defined by focusing, for example, in this cell, so this will be the center, the north cell will be this one, the east cell is this one, here we define the south cell, and the west is this one. Thus, the neighborhood here will be defined according to these cells. Now, let me show you the training process for the cell in the center of the grid. This process is the same process that is run in parallel for all the cells in the grid. Thus, as we said before, we define a subpopulation according to the neighborhood relationship. Here we can see the networks that will be part of this subpopulation. So, each cell sends its networks to the center. This way, we create the two subpopulations. We have the subpopulation of generators and the subpopulation of discriminators. Now it starts the evolutionary process of our competitive co-evolutionary algorithm. Using a reduced number of mini batches, for example 1, we compute the loss of all of our models. According to this evaluation, we select the best pair of generator and discriminator. This selection process can be applied by using different kind of operators like roulette wheel, tournament selection. In our case, we use tournament selection. These pairs are evolved during this generation or training epoch to create the offspring. The offspring is created by applying an SGD-based mutation operator, which means that we apply backpropagation method as any other GAN training process to update the parameters of our two models. In order to do so, we train the networks by using all the training dataset mini batches. After this training, the offspring networks are included in the subpopulation. After that, the subpopulations are evaluated again. Then we remove the least competitive one, and the best one is located at the center of the cell. As it can be seen, the center has been updated. Then the center will be sent to the cells in the neighborhood to allow them to update their own subpopulations. After that, they will use this new network to their training process. As the other cells are also applying in parallel their own training process, at some point they will update their own centers, and then they will send their centers to our cell to update our subpopulations. This is asynchronous. Our training method doesn't wait for the neighborhood updates to continue its training loop. This training loop is repeated until a given stop criteria is reached. At the end of the training process, we will have trained a subpopulation of generators and a subpopulation of discriminators in each cell. So why don't use all of the generators to create a generative model as an ensemble of generators? This idea has been motivated because it has been proven that the use of ensembles or mixtures of models provide better results in many different machine learning problems. Thus, the generative model consists of the generators of the subpopulation and a vector of mixture weights. The mixture weight I represents the probability that a given data sample comes from the ith generator. In order to find the best combination of weights to optimize the quality of the generated samples, we use evolutionary strategies. The quality of the generated samples can be measured in terms of inception score, FID score, etc. So, at the end of the training process, we will have, for each cell, a generative model which is composed by the generators and the mixture weights and a subpopulation of discriminators. Among the all generative models computed in all the cells, Lipizzaner returns the one which is able to create the best data samples. This was the summary of the main steps of Lipizzaner algorithm. Don't forget that the source code is freely available in GitHub. This is the link. You can clone it and start using it to train your own generative adversarial networks. You have much more information in the description of this video, and please don't hesitate to contact us if you have any question.